Okay, so this is where we're going to start looking at some examples on solving a log equation. And these are the properties we're going to use. So remember, one of the things that you learned in a previous topic, probably last week, was that you can always change a log equation to an exponential, all right, and vice versa. So you see where it has log of x base b. So remember, your base is listed as a subscript, so log of x base b equal y. You can always change a log equation to an exponential. So it's always the base raised to this power equals, and notice that this, we're going to call this the argument, So let me just write the word argument for right now. So the argument is what you're taking the log of. So that's going to go over here on the other side of the equal sign. All right, so as we go through this, you're going to see how this is used. Then we're going to use a product rule. So the product rule says this: if you take the log of a product, m times n, then you can always write it. You can write the log of a product, so we're expanding it. So this is called expansion. So we're expanding it to the sum of each individual log. So the log of m plus the log of n. So the log of a product becomes an addition problem. Quotient rule, that's where you have the division right here. So the log of a division becomes a subtraction, becomes a difference of two logs. You have to remember, though, that the numerator is the first one you see, and the denominator is the second part that you see. So the log of m divided by n base b is the difference of the log of the numerator and the log of the denominator. Notice the base. You need to write the base. So as we go through this, you're going to see I'm going to write those bases. If you leave those bases off, it's understood to be 10. So we're going to talk about that as well. Then you can also use the power rule. So the power rule says this: if you have the log of some argument raised to a power, you can always take that power and write it out in front as a product. So you're going to see that as well. And then there's something called the one-to-one property of logarithms. And the one-to-one property of logarithms says if you have two logs equal to each other, like you see right here, and the bases are the same, so the bases have to be the same, then the arguments are equal. So m must equal n. So you're going to see that as we go through these examples. All right, so let's look at example one. So let's solve this log equation. So the first one's going to be this, and it's going to be the log base 3. So notice the base is always a subscript. So if this was lined paper, you would write it like this. You would say log base 3, like this, of, in parentheses, 2x plus 1 equals 2. So that's how you would write it. So see, lined paper, this is horizontal. Your base is a subscript. So make sure that's how you write logarithms. All right, so keep that in mind. All right, so this would be log base 3 of 2x plus 1 equal 2. All right, now, so notice, in every problem we do, it's going to end up looking like this. So where you have the log on one side, and you're going to have, in our cases, a number on the other. And so whenever you have a log on one side, you're going to use number one, definition of a logarithm. So you're going to change a log equation to an exponential. You're going to change a log equation to an exponential. All right, so remember, the base, you're going to just how you say it, base raised to this power equals the argument. So b to the y equal x. So let's look at how you're going to do this. So this is an easy one. So this is an easy one. I'm putting that one so that way you can see how to use this property right here. So the first thing you look at is the base. What is the base? Well, the base is 3. So you're going to say 3 raised to the second power equals the argument. And the argument is what you're taking the log of. I'm taking the log of 2x plus 1. And there's your equation. And all you do is solve, and notice that in this case, I want you to see something. I went from a log equation to a linear equation because 3 squared is 9. 9 equals 2x plus 1. This is linear. Solve for x, and you're done. Subtract 1 from both sides. I get 9 minus 1 is 8. 8 equal 2x. Divide both sides by 2. I get x to be 4. All right, now one thing I got to tell you though. When you think about the log of x, if you think about when you're taking the log of x, I'm going to use, now remember, one of the things you learned was that if there's no base listed, it's understood to be base 10. So this is base 10 that we're looking at. If there's no base listed, it's understood to be base 10. And your calculator, if you look at your calculator real quick, so you see right here, let me find it. Right here, see that LOG? That's the button you use if it's base 10. Right here, LOG base 10. So I want you to see something. If I take the log of 6 and approximate this using my calculator, so I'm going to say log of 6, and I'm going to parentheses, press equal. So that's about 0.7782, right? So 0.7782. If I take the log of, let's say 1/2, 0.5. So the log of 0.5, press equal, that's negative, so that's about negative 0.3010. So round, usually they'll ask you to round to 4 decimal places or so, but 1, 2, 3, 4, since 2 is less than 5, the 0 stays 0. But here's what I want you to see. If I take the log of a negative 2, so if I do log negative 2, notice what happens. You get an error. So that means that the log of a negative number is not a real number. The log of a negative number is not a real number. You cannot take the log of a negative number, and here's why. So watch. If I look at this, the log of x equal, let's say 100, okay? And if I change this to an exponential, remember the base right here is understood to be 10, so you say, let's do 2 right here because 100 is too big. If I say 10 squared equal x, right? So remember the base is always a positive number and cannot equal 1. So a positive number raised to any power, is always positive. So a positive number raised to any exponent, any real number, is positive. So you see this x right here, which is 100, is positive. So that's why the argument must always be a positive number. So you can only take the log of a positive number. You can only take the log of a positive number. Okay, so that means that the domain of a logarithm, and I'm going to write it as log of x, the log of x. So the domain of a logarithm is any real number that's positive. So x must be greater than 0. So what you have to do here is this now, and you're going to notice we're going to do this in all these examples. Once you solve for x, all you have to do is check and see if this value of x makes this argument negative, because it cannot be negative. We just saw that you can't take the log of a negative number. So all you have to do is look at this argument. 2 times 4 is 8. 8 plus 1 is 9, right? And look, is 3 squared equal to 9? Yes, it is. But that's all you have to do is just check it. Once you get x by itself, just go back to all of your arguments that have variables in it and see if it makes it negative. All right. But in this case, all you had to do is, since you had one logarithm by itself, then you just use this property right here, where you change a logarithm to an exponential and you solve for x. All right, so let's look at the second one. So number 2, let's suppose this was number 2. So it'll be another one like this, just to kind of get us into using that first property. So the log of x minus 10 base 5 equals 2. All right, so once you have the logarithm by itself, then you can use that property. You can change this log equation to an exponential. Always change a log equation to exponential. So you're going to say the base, which is 5, raised to this power, so I get 5 squared, equal the argument, which is x minus 10. So I've changed this log equation to this equation, to an exponential, which really in this case is actually linear. So I get 5 squared is 25, equal x minus 10. Solving for x, I'm going to add 10 to both sides. I get x equal 35. Now you got to check real quick. Just check the argument. Is the argument be negative? 35, see x is 35. So 35 minus 10 is not a negative number. 35 minus 10 is positive. And so therefore that's going to work. And you can always check real quick. 35 minus 10 is 25, right? What's 5 squared? 5 squared is 25. Now let's look at this one. So this is going to be number 3. So number 3, we have, all right, we have this problem. Okay, we have the log of x base 4 plus the log of x minus 12 base 4 equals 3. Okay, now remember, in order to use this property, the definition of a logarithm, in order to change a log equation to an exponential, you have to have one log. You have to have on one side the term with just the word log in it, L-O-G. The problem here is that if you notice this problem, on the left side there are 2 logs. So I cannot go directly to changing this log equation to an exponential. I cannot change this to an exponential. In order to do that, I've got to get this to be one logarithm. And to do that, you're going to use the product rule. So if you go backwards, you see this right here? That kind of looks like this, right? So if you have the sum of 2 logs, now they have to have the same base. If you have the sum of 2 logs, then that means you can write as a product. And you have that one log. You have a single logarithm. So since the base is the same, then this becomes the log base 4 of the product of the arguments. So it'll be x times x minus 12. The product, this times this, is what you see here. And then that's equal to 3. And now notice, I have a single logarithm. Once you have a single logarithm, you can now use this property. So I went from 2 logs to a single logarithm. Notice the base, you have to write the base. The base is important here. So now let's change it to an exponential. 4 raised to the 3rd power. 4 raised to the 3rd power equal x times x minus 12. So 4 raised to the 3rd power equals the argument. Okay? All right. Now, when we did the previous problem, when I changed this single logarithm equation to an exponential, I ended up with a linear equation, right? Notice what this is. This is not linear. If you distribute, that's quadratic. All right, but keep in mind that 4 cubed, you got to figure out what that is. So if you can't do it real quickly in your head, then just use your calculator. 4 raised to the 3rd power is 64. So I get 64 equals x squared minus 12x. Okay? So 64 equals x squared minus 12x. So this is quadratic. So now you got to solve this quadratic equation. So let's go ahead and bring the 64 to the other side. So I get 0 equals x squared minus 12x minus 64. And the ones you're going to have are going to be factorable. So these are going to be factorable. So let's go ahead and factor. So I get 0 equals, all right, now let's see, that's x times x. For 64, let's try 16. Let's see, 64 divided by 16. 64 divided by 16 is 4. See, I want that 12 right here, right? So what's going to work is it'll be 16 and 4. And remember, the last sign's negative, so these have to be different, and the larger will be the negative. So this has to be negative, this has to be positive. And double check, negative 16 times 4 is a negative 64. The outer is 4x, the inner is negative 16x. When I add them up, I get negative 12x. Now, once you factor, you're going to set each of those factors equal to 0. So get x minus 16 equals 0, x plus 4 equals 0. And you solve for x. X equals 16, x equal negative 4. Now remember, you have to check, right? You always go back to the original. So you see the original, there are two arguments. You have this and you have this. You can only take the log of a positive number. You can only take the log of a positive number. So let's check 16 first. 16, when I substitute 16, that's positive, right? When I substitute 16, what's 16 minus 12? Well, that's 4. That's positive. So we're good. So if I did this work correct, then 16 works. Negative 4, though. Let's look at negative 4. The log of negative 4. Well, I cannot take the log of a negative number, so right away I know this is not going to work. So I'll cross it out. And you could even use it here as well. Notice negative 4 and negative 12 is a negative 16. I cannot take the log of a negative 16. So you see, if this was base 10, which is not, it's base 4, but if this was base 10, notice the log of negative 16 is undefined. So that's why you get an error there. So that's all you do. That's all you have to do to check. So on your final, though, you will end up with a quadratic one. With a quadratic. So you're gonna have something like this, either subtraction or division, and it will be quadratic. So you have to factor, all right, and then always make sure you check your answers, your proposed solutions, I should say, in the original. Remember, you cannot take the log of a negative number. All right, let's look at another. So this is gonna be number 4. So it's not that difficult. It's just using your properties. All right, number 4, let's do a subtraction. So let's look at this one. We have the log of x plus 1 base 2 minus the log of x minus 4 base 2 equals 3. All right. Now remember, before I can change the exponential 3 to a power, I have to have a single logarithm all by itself. Before I can use this property, property number 1, I have to have a single logarithm all by itself. I don't have that here. I have 2 logs on one side. But I do know that there's something called the quotient rule. So the quotient rule says if you take the log of a quotient, then that becomes the difference of the numerator and the denominator. So if you look at this, that's this right here. So using the quotient rule, I can rewrite this as a single logarithm. Now always remember though, when you subtract, subtraction matters, the order in which you subtract matters. So notice that m is a numerator, n is the denominator. So when I rewrite this, this is going to be your numerator, and this is going to be your denominator. So look how this is going to look. You have the log base 2 of x plus 1 divided by x minus 4. See the log of the numerator minus the log of the denominator. That's what you see here. Equals 3. And now I have a single logarithm, so I can rewrite this as an exponential. 2, always put your base first. 2 is your base raised to this power equals the argument x plus 1 divided by x minus 4. And 2 to the third power is 8, so I get, I'm going to transpose the sides, so I get x plus 1 divided by x minus 4 equals 8. And then all you got to do is solve this rational equation. You had one of your tests on test number 4. Now test number 4, the rational equation was harder than this one. This is a lot easier than the one that was on test number 4. So you can clear the fractions. So the LCD is x minus 4. And so you multiply both sides by x minus 4. So watch what happens. So you say times x minus 4 times x minus 4. And then these divide out. And you get x plus 1 equals 8x minus 32. So I want you to notice I went from this log equation to a linear equation. And so I'm going to just subtract x from both sides. And so I get 1 equals 7x minus 32. Adding 32 to both sides. I'm running out of room, so I'm going to put that here. 32 plus 1 is 33, equal 7x. Divide both sides by 7. I get x to be 33 divided by 7, which is a mixed number. If you want to write as a mixed number, because you do have to check. If you write as a mixed number, 7 goes into 33, what, 4 times? Yeah, 4 times, so 28 with a remainder of 5. So you get 4 and 5 sevenths, or 4 and 5 sevenths. All right, but remember, you got to check. You got to make sure that the argument is positive. So watch, 4 and 5 sevenths, right? Always go to the original. Is 4 and 5 sevenths plus 1 still a positive number? Yes, it is. It's 5 and, what was it, 3 sevenths? 5 sevenths? Is 4, remember, 4 and 5 sevenths, is 4 and 5 sevenths minus 4 still positive? Yes, it is. It's, what, 5 sevenths? So it's still positive. So this is it. This proposed solution will work. As long as you did the algebra correct, then all you have to do is check this into the argument. The argument must be positive. All right, so that's number 4. So notice addition becomes multiplication. Subtraction becomes division. So here we use the product rule. Here we use the quotient rule. So product rule, quotient rule. Okay? All right, let's look at number 5. So let's suppose in number 5, we have this problem. Let's say we had this one. Let's do an addition one again. So it'll be log base 9 of x minus 5 plus the log base 9 of x plus 3 equal 1. All right. So notice I cannot change this to an exponential because that's not a single logarithm. But I see this addition here. The bases are the same, so I can write this as a single logarithm. I can write this as a single logarithm. So it'll be the log base 9 of the product. Addition becomes product. So you're going to multiply the arguments together. So it'll be x minus 5 times x plus 3, and all that's equal to 1. So the first thing you're going to do is you're going to change the sum of 2 logs. As long as the bases are the same, you're going to change the sum of 2 logs to a single logarithm, but the argument here is a product now. And now since that's a single logarithm, I can change it to an exponential. 9 to the first power. 9 to the first power equals the argument. X minus 5 times x plus 3. And so now look though, you got to get rid of these parentheses, right? So you're going to FOIL. And when you FOIL, do you see that this is quadratic? So you're going to factor at some point. So I get 9 to the first is 9 equal x times x is x squared. The outer is 3x. The inner is a negative 5x. And the last, a negative 5 times 3 is a negative 15. Combining like terms, I'm going to transpose the sides. So combining like terms, I get x squared. A positive 3x and a negative 5x is a negative 2x minus 15 equal 9. And then I'm going to bring 9 to the other side. So I get x squared minus 2x. Negative 15 and a negative 9 is a negative 24 equal 0. All right, and then remember the ones on your test will be factorable. So let's go ahead and factor this. And if you have trouble factoring, just use the quadratic formula. So I get x, and then what's going to work for 24, so that I can get a negative 2x as a middle term, what's going to work is that you're going to say x minus 6 times x plus 4. And you'll always check. The outer is positive 4x, the inner is a negative 6x, and I get that middle term, negative 2x. So now we're going to set each factor equal to 0, just like this. And so I get x to be 6, x to be negative 4. Now remember, you got to check those into the arguments to make sure that they're positive. So look, 6, let's try 6. Is 6 minus 5 positive? Yes, it is. Is 6 plus 3 positive? Yes, it is. So this is going to be good. Let's look at negative 4. Is negative 4 and a negative 5 a positive number? No, it's not. It's a negative number. So right away, I cannot use that. So remember we talked about the ideas of extraneous solutions, false solutions. So negative 4 is a solution to this quadratic, but it's not a solution to the log equation because it makes my argument negative. And you remember we cannot take the log of a negative number. So that's how you do number 5. So if you can do something like that, then you should get those points on the final exam. So let's look at another one. So let's do number 6. So this is number 6. So number 6, let's do a subtraction. Let's suppose we had the log base 3 of x plus 25 minus log base 3 of x minus 1 equals 3. All right, so remember, I can see you have this log equation. So to solve a log equation, you want to try and change it to an exponential. Well, to change it to an exponential, you have to have a single logarithm. That's not what you see here. So you want to rewrite this as a single logarithm now. But notice you have a subtraction here. So remember, subtraction becomes a quotient. So you can use a quotient rule. So you're going to say this. You're going to say the log base 3 of the numerator is going to be this first argument, and the denominator is the second one. That's 25, equal 3. And now, since I have a single logarithm, I can change it to an exponential. So I can get rid of those logs by changing it to an exponential. So I get 3 to the third power. So 3 to the third equals x plus 25 divided by x minus 1. Okay. And so now you got to figure out what this is. 3 to the third is 9. So I get 9 equals x plus 25 divided by x minus 1. Okay, so now we have this rational equation. So let's go ahead and multiply both sides by the LCD, which is going to be x minus 1. Let me go ahead and rewrite this. I'm going to multiply both sides by x minus 1, x minus 1. Now if I distribute here, I get 9x minus 9. 9x minus 9 equal, these divide out, and you get x plus 25. So notice I went from a log equation to a rational equation to a linear equation. Okay, so let's go ahead and subtract x from both sides. So I get 8x minus 9 equal 25. Adding 9 to both sides. So I get 8x equal 25 plus 9 is, what's that, 34? So I get 34. Divide both sides by 8. And if I reduce, I get x to be, let's see, 35 divided by 2 is what, 17? And then 8 divided by 2 is 4. So you get 17 fourths, which is, as a mixed number, 4 and 1/4. So you get 4 and 1/4. Okay? All right, now you got to check this though. So you got to go back to the argument. So that's one of the things you got to remember to do is check. Okay, so remember 4 and 1/4, right? So is 4 and 1/4 plus 25 still a positive number? Yes. Is 4 and 1/4 minus 1 still a positive number? Yes. So if I did this algebra correct, then 4 and 1/4 or 17 fourths is our answer. All right, so that's number 6. So fairly easy. It's not difficult. It's just knowing how to use those properties. Let's do another subtraction. So we have the log base 7 of 2x minus 3 minus the log base 7 of x plus 2 equal 1. All right, so remember, I have this log equation. I want to change it to an exponential. In order to change it to an exponential, I have to have a single logarithm. Well, since the base is the same and this is division, subtraction, I can use the quotient rule. So I'm going to get log base 7 of the numerator, denominator. So it'll be 2x minus 3 divided by x plus 2, and all that's equal to this side, which is 1. Now, since I have a single logarithm, I can change it to exponential. So it's your base raised to this power equals the argument. So 7 to the first equals 2x minus 3 divided by x plus 2. So 7 to the first is 7, so I'm going to rewrite this as 7 equals 2x minus 3 divided by x plus 2. Okay, so now I'm going to go ahead and clear the fractions. I'm going to multiply both sides by x plus 2, the LCD. And so if I distribute the 7 here, I get 7 times x plus 2. So that's 7x plus 14 equal, these divide out, you get 2x minus 3. So notice I have this linear equation. So I'm going to go ahead and subtract 2x from both sides. So I get 5x plus 14 equal a negative 3. Subtracting 14 from both sides, I get 5x equals a negative 17. Divide both sides by 5. I get x to be a negative 17 fifths, or as a mixed number, 5 and a 17 is 3, 3 times 5 is 15, remainder 2. I get 3 and 2 fifths, negative 3 and 2 fifths. Okay, but you got to check, because you're trying to solve a log equation. Remember, you can only take the log of a positive number, so these arguments must be positive. So let's check, negative 3 and 2 fifths. 2 times a negative 3 and 2 fifths, and you may say, well, that's complicated. It doesn't matter, right? Because look, a positive times a negative is a negative, right? And a negative is still what? A negative. So you're taking the log of a negative number. So right away, you know that this is not a solution. You could have also gone here. So negative 3 and 2 fifths plus 2 is a negative 1 and 2 fifths. So right away, you know it's negative. So this is not going to work. But then you may say, well, what do I write? Because when we did, I want to show you again. When we did, real quick, when we did this one, remember we had 2 proposed solutions? This one did not work, so this was the only one I could say is a solution, right? So we did have a solution, was this one. You might say, well, I don't have 2 proposed solutions here, I only have 1. Okay, it didn't work, right? So you're going to say no solution. That's what you say, no solution. So this equation right here has no solutions. This equation, when I checked it, only has how many solutions? 1. This one did not work, this one does. This had 1 proposed solution, it did not work, so I say no solution. All right, so just keep that in mind. All right, that's number 7. Let's do one more in this group. So this is going to be number 8. So let's do number 8. So let's do an addition one. So let's do a sum. So we have the log of 5x plus the log of x minus 1 equals 2. So remember, you have this log equation. I want to change it to an exponential. Before I can change it to an exponential, I have to write this as a single logarithm. Since the bases are the same, and notice right here, you don't see any base listed, right? In all the other problems, you physically saw a base for 2. Here, there's none. Remember, if the base is not there, it's understood to be 10. So if you see something like this with no base, that's understood to be base 10. That's called our common logarithm. Common logarithm, that's what that's called. So whenever you have base 10, that's your common logarithm. All right, but it doesn't matter. You're going to do the same thing we've been doing. So since the base is the same, you're going to write this as a product because you're adding. So you're going to say log of 5x times x minus 1 product. So this times this is what you see here equals 2. And now, since I have one logarithm, a single logarithm, I'm going to change this to an exponential. What's the base? You don't see anything, right? What's it understood to be? It's understood to be 10. So remember, log, the log, that's understood to be base 10. So you're going to say 10 to the second power equals 5x times x minus 1. And then you figure out, well, 10 to the second, that's 100. So I get 100 equals, and then distribute here, I get 5x times x is 5x squared. And then 5x times a negative 1 is a negative 5x. All right, so notice I have a quadratic, I have a quadratic equation. So let's go ahead and bring everything to one side. So I get, let me go ahead and transpose the sides first. So I get 5x squared minus 5x equals 100. So let's subtract 100 from both sides. I get 5x squared minus 5x minus 100 equal 0. And I want you to notice all of these, you see the GCF here is 5, right? 5, 5, negative 5, negative 100. They're all divisible by 5. And since this is an equation, since I have an equation, I can divide both sides by 5 to make this a simpler quadratic, because that's an equation. So what you do one side, you do the other. You can, if you divide the left side by a number, you do to the right hand side as well. So I'm going to go ahead at this point. I'm going to go ahead to make this easier for me to factor, and you don't have to do that. You can go right away. You can go right away and factor. But the problem is that this is 100 and this is 5, so it's a little bit more difficult to factor. But what I'm trying to make this point is that if you notice, I have this equation. There, all these terms here, the GCF is 5, so I can divide both sides by 5. What I do one side, do the other, and now notice 5x squared divided by 5 is x squared. A negative 5x divided by 5 is a negative x. A negative 100 divided by 5 is a negative, what's that, 20 equals 0. And see, that's easier to factor. So if I factor, I get x minus 5 times x plus 4. And then I set each factor equal to 0. So I get x minus 5 equals 0, x plus 4 equals 0. And so I get x equal 5 and x equal negative 4. Now, notice you have two proposed solutions you got to check. So let's check the 5 first. When I go to 5, you got to go back to the argument. 5 times 4, I'm sorry, 5. 5 times 5 is positive. 5 minus 4 is positive. So this is going to work. Let's check negative 4. 5 times a negative 4 is negative. So right away, I know this is not going to work. So this is the only solution. X equals 5 is the only solution. Most of you probably would not have done what I did. Most of you would have saw this quadratic equation and you would have tried factoring. And if you had difficulty factoring, you would have used quadratic formula. Quadratic formula would have given you these two. So if you tried factoring, you would have said 5x, x, right? And then for 100, you would, there are several possibilities. You could say 10 times 10, 50 times 2, 20 times 5, right? So let's try 20 and 5. So let's put 5 here and 20 here, because 5 times 20 is 100. The last sign's negative, and the middle sign's negative. The middle term, rather, is negative. So that means the larger of these has to be negative. So it has to be this one. So let's see if that's going to work. So that's, so, no, the way I have it is not going to work. So let's try, because look, 5x times 20 is what, 100x? And that's a lot smaller than 100. So let's change it. So that's not going to work. Let's try, let's try 10 and 10 and 10. See, no, that's not going to work either. Let's try, let's try, see how easier it would have been just to go ahead and divide it by 5? All right, so 5 and 20 won't work. So let's try, let's do 10 and, that's not going to work. 10 and 10 won't work either. So let's do, okay, let's do 4 and 25. So let's put 4 here, 25 here. So notice that the outer is 20x. Okay, that's going to work, because look, the outer is 20x, the inner is 25x. When I subtract them, I get 5. But this one has to be negative, and this has to be positive. All right, so that's how you factor this if you did not divide both sides by 5, or if you did not factor out a 5. And then you would set each factor equal to 0. So what? If I set each factor equal to 0, I get 5x minus 25 equals 0. 5x equals 25, x equals 5. And that's what we got here, right? Over here, x plus 4 equals 0, x equal -4, and that's what I got here. All right. So just know that if you're dealing with a quadratic equation and you have a GCF other than 1, I would just go ahead and divide both sides by that number to make this easier to deal with. Okay, you could have also done this, just to let you know. So rather than trying to factor everything as you see, you could have factored out a GCF of 5. So you could have said, well, that's going to be 5 times x squared minus x minus 20, right? Factor out of 5, and now notice this looks like this. And so now this becomes 5 times, and then you factor, so you get x minus 5, x plus 4, and remember that's equal to 0. And then you said each factor equal to 0. The problem is that this factor doesn't have a variable in it, so you don't even use it. So you're just going to use these two because these are the only ones with variables. So you can say x minus 5 equals 0, x plus 4 equals 0. And then now that looks like this. All right, so multiple ways you could have gone with this one. But the point is, though, that you had to change this to a single logarithm, and that since this is addition, you would write as a product, and then you change it to an exponential, you get this quadratic, and you solve this quadratic equation. All right, so that is the first part of the review. So we took us about 40 minutes to talk about these 8 problems. All right, so let's look at this one now. So let me go ahead and turn this one off.